Hey everyone, how you doing? It's me, Clara, and I'm back with a new series of videos. So these are science chats. Basically, I am inviting on friends of mine that are basically they're great scientists. They do lots of really interesting research, and I don't really necessarily know much about that research. So I'm trying to find out what it is they do and how they do it and stuff like that. And also, I want to chat to them. They're on here because they also are active in trying to improve equity in STEM for people from different backgrounds. So they're all amazing activists. I mostly want to talk about their science. I'll mention a little bit about the sort of diversity work, but that isn't the focus. The focus is their science. And yeah, like I say, I just want to figure out what it is they do because I don't necessarily know that well. Today, I'm going to have a friend of mine, Dr. Andrew Princep. He is a physicist at Oxford University, and I'll put some links below for a webpage that they're on and also their Twitter links. It's worth following them. And I will say it'd also be kind of cool if you could sort of do the whole sort of subscribe and like thing. That'd be really helpful for a small YouTuber like me. But you know, and yeah, and so with that, let's get into the interview, I guess. So let's bring in Andrew. Hey, how you doing, Andrew?
Hi, I'm doing really well, thank you.
Good. So, Dr. Andrew Princep, do you want to introduce yourself? Tell us about you. Who are you?
Yeah, I am Dr. Andrew Princep. I am a physicist. I do research at Oxford University and also the Rutherford Appleton Laboratory, which is just near Oxford University, which is a national research lab for large-scale science. And my work mostly focuses on what we call quantum materials. So really, this just boils down to materials where some kind of quantum effect is important to how they work or why they work. Although it's one of those things where if you want to be really pedantic, more or less every material has the property it does only because of quantum mechanics, because ultimately a material is a collection of atoms which interact with each other via quantum mechanics. But generally speaking, we're interested in exciting properties like magnetism or superconductivity or something like that.
Yeah, I was just pulling together a presentation on the history of superconductivity, and obviously the stuff with Rutherford Appleton Labs is a big thing, and the cables, and I've just been going into that. And also, I've also had to go into discussing magnetic spin in more. I got a crash course in magnetic spin yesterday, basically. So I'm still a little bit hazy on it, but I know more than I did yesterday, so that's probably a good thing. I like to learn.
It's one of those things, yeah. Like nobody really, in my field at least, cares why it exists, just that it does.
Yeah, that's true. I'm literally just talking about the spin, but yeah, I'm talking about MRI scanners and just trying to get them all to line up. The spin's in line, but anyway. But also,
I was going to say, actually, on the topic of Rutherford Lab and superconducting coils, I did actually get to hold the first superconducting coil magnet that was ever built.
Oh, wow.
Because they have it sitting in Oxford. It was in some guy's office.
That sounds about right, actually. That was a big reason why we were able to start the Centre for Applied Superconductivity in Oxford, because there's so much activity in Oxfordshire. And our lab was a collaborative project with sort of industry. Well, still is. I don't know why I'm saying was. Past tense. I'm talking like it's dead. So, yeah, there's a lot of superconductivity going on. And like I say, I've been putting a lot of... And I've been trying to animate it all recently, which is really fun times. And before we get into the science a little bit more, I've also invited you on. Obviously, you're a friend of mine, but also you're an activist for sort of diversity in STEM. And we'll go into that more later on. But is there, just to introduce people to some of the work that you're doing in sort of the outreach and diversity field, what are the main points?
I guess the main points for me are probably like, I am a gay man, so I do a lot of work on LGBT issues in academia. And as such, I'm part of the inclusion group for equity and research in STEM as IU. And we sort of try and broaden the respect for diverse people doing science, and the sort of effort that people go to in making their contributions welcome and amplifying their ability to contribute to science, basically, and or just to, like, you know, enjoy existing in the space of academia.
Yeah, that's very true. And hopefully it's a little bit more, you know, it's not just academia, but STEM in general. But yeah, definitely. And it's thinking about it, we actually met at a conference, the LGBT Seminar, which is sort of 3-4 hours away a few years ago. Not in Oxford, go figure, but we did have a long train ride back where we got to talk board games, which was pretty cool.
Yeah, I should confess, I did know you by reputation before then, because of course you are a large figure in Oxford diversity circles. So
yeah, I have been eating a lot of ice cream. I actually got some ice cream yesterday that's got soy in it, and I'm allergic to soy, but it's my favourite ice cream, and I'm just like, I'm not leaving the house for a few days. I can deal with a bit of discomfort, which is, well, that's anyway.
I only had soy ice cream once when I was in Tokyo, and it was a truly, like, sublime experience. So I can understand why you went out of your way to have it.
Well, this isn't even soy ice cream. It's just that so much chocolate has soy lectin in it, and that still upsets me. So I'm pretty sensitive. I'm so sensitive. Yeah. So it's actually the chocolate. Ben and Jerry's peanut butter cup. I love it. I would say that my favourite is Ben and Jerry's Cherry Garcia, but you can't get that anymore. So, and that one I'm not allergic to. I need to start a campaign.
Yeah, bring it back. Respect my dietary restrictions.
Yeah, exactly. It's a shame, they're really good at so many things. But anyway, so completely off topic. So you're working in the physics department and Rutherford Labs, like you say. So, little bit more about what you're doing. What are the basic things that you're trying to find? What sort of materials are you working with? What's your overview?
So most of my work early on was in rare earth materials. I was looking for things where not just the magnetism was important, but also when we talk about, like, atoms being sort of spheres or spherical-ish, or they have some sort of, like, density of electrons around them, often that this is kind of spherical. But I was really interested in materials where it was kind of pancake-shaped. And if you have a bunch of atoms which are sort of sat next to each other and they're spheres, it doesn't really matter. Like, if you rotate them, it's kind of the same. But if you have atoms which are pancakes, then it matters what alignment they have, because they kind of don't want to be like this, but they'll very happily be like this or like this. And this can have some profound ramifications for the electrical properties of the material. And that was what I did my PhD work on. Mostly using the technique of neutron and X-ray scattering, mostly X-ray scattering, actually, because X-rays are very sensitive to the shape of the electrons around atoms, and neutrons are more sensitive to the magnetism. Then I kind of moved into more hot topic areas, I would say, because it was a real big thing for the last 5 or 10 years. To look at, basically, we feel like we've moved past magnetism in the transition metals, the regular transition metals, so like iron, copper, nickel, etc. Those are boring, those are 30, 40 years ago. So now we've moved on to the real exotic stuff, like osmium, like iridium, stuff which is hideously expensive and more complicated, because when you're in different bits of the periodic table, different forces matter more or less. And one of the balance of forces in elements like osmium and iridium and so on are very close together. So you're not dominated by, say, the repulsion between electrons. your relativistic effects are also important, and some other effects are also important, and everything is sort of about the same. And so even a tiny, tiny difference leads you to very weird and unusual behavior. And we like weird and unusual because sometimes it can tell us things that are new, and sometimes it just allows us to look at something which you just don't get very often. And even more recently, I got into going back to regular transition metals because the chemistry is far easier. But what if I didn't want to just get whatever crystal somebody could make me, but I wanted to say, I want a crystal that at the atomic scale looks like this, and not be stuck with like, oh, well, the distance between my iron atoms is this, and so their interaction is this, and I can't do anything about that, short of like squishing the crystal between like with like the pressure of 1,000 atmospheres or something. What if instead the thing that separates my iron atoms is an organic molecule, and I can change that organic molecule? And when I change it, I can change the strength that the iron atoms talk to each other with, or I can change the distance between the iron atoms, and I can change the geometry that my iron atoms have. Like, are they sort of connected to each other in a big triangle, or do they sit at like the corners of squares or something like this, like hexagons, you name it. In principle, you could have it. And I became really fascinated with the ability of certain types of chemistry to just give you the kind of crystal that you want if you choose the right organic molecules to link your metals together. And this is allowing us to explore some really difficult to access physics because you have this control of the lattice. You're not just stuck with whatever like metal oxide chemistry gives you. And this has allowed me to also team up with some people who do machine learning. And they're with this huge space of chemistry and the huge searching power and matching power of machine learning. They want to be able to predict what properties materials will have based on a couple of simple rules. And I would like to be able to find more things that have the physics that I find really interesting. So if they're able to say, look here, and I'm able to get somebody to make me that thing, and then I can go and measure it and say, yes, it does or doesn't, everybody wins.
That's awesome. That's interesting because I'm sort of putting stuff together and seeing whether we can change the properties of them depending on how we try and smush them together. But you're really trying to make designer materials, basically.
Emphasis on the word trying.
Always. That's science. We've been doing this long enough to know that. Anyone that thinks you're going to get wins all the time in science is sadly naive. And we need to be realistic, unfortunately. But we are trying, and every so often you have those amazing breakthroughs. One day we'll have our graphene breakthrough, I'm sure.
I mean, graphene did have that really exciting breakthrough 2 years ago now, I guess, when they developed the twisted bilayer graphene.
Yeah, there's still a few more things to discover, and that's the great thing about science. There's stuff to discover. I mean, there's still so much that we don't know, and that's why I find it really exciting. You know, there is still options, but
but like literally when that like discovery happened, most of the people who I work with just lost their minds. Because the idea that if you like stack two graphene sheets on top of each other and you twist one by like 1.1 something degrees, and then suddenly you go from graphene being an insulator, which is kind of boring in my opinion. I didn't say that. And then it's a superconductor. And depending on how like the voltage you apply, it can be a superconductor or an insulator, possibly a magnet. And it just like literally all of the physics that people in my area care about can be accessed just by like twisting these graphene sheets and applying an electric field. And it was just like, my goodness, this is an amazing playground.
it opened up a lot of possibilities, and it was really good. I don't know, it had a big social impact as well. Just, I mean, the initial discovery of graphene, and further, like, people have heard about it, which is quite unusual, I feel, for a lot of the stuff that I do, when people actually have a basic understanding that this thing exists. Plus, you know, a lot of discovery in Manchester, and I'm from Manchester, so I'm not going to lie, that's kind of nice. And I probably should know more about it than I do.
Well, I mean, Andre Geim is a hero, right? Because he's the levitating frog guy as well.
Yeah.
So,
yeah. Forgot about that. Oh, yeah.
The only physicist to have a Nobel and an Ig Nobel.
Yeah, that's levitating frogs. I'm going to struggle to get that out of my head for a little while. Sorry.
Sorry.
I'm so easily think. I mean, I still. You'd think that I've been doing this for so long that I wouldn't still laugh as a trans person when I hear transition metals, but you know. Okay.
I mean, transuranics is even better, right?
Yeah. Yeah, that's coming up. Anyway, no. So the materials. So some of the earlier materials that you were talking about materials like osmium. You were saying that they were quite expensive and rare. So why are they of interest? You know, what would you use them for? Are they practical? Are they things that we can actually use?
Well, this is always the sort of fundamental tension, because I don't like to stress too much about whether or not my research is practical, because then I might not do it. And any discovery that you make can in principle be applied elsewhere. Even if it seems at first that it only applies to the system that you're looking at. For instance, nobody would have imagined that we'd be looking at superconductivity and sheets of twisted carbon, even though a lot of superconductors that people look at are very expensive and complicated materials. And osmium is a particularly interesting one because osmium is expensive. Not like grossly expensive, but hundreds of pounds a gram expensive. And I think most of it comes from China. There's like supply issues related to getting hold of it sometimes.
That sounds about right, yeah.
And the other thing is, of course, that osmium is quite famous amongst chemists for causing horrific injuries and death. Because osmium metal is fine, but osmium is one of these weird elements that can have a very wide variety of oxidation states. So in chemistry, osmium exists from like -2 to +8 as oxidation states. Like, you name it, there is an osmium compound somebody has made which has that oxidation state. And the +8 one, unsurprisingly, can do some stuff. Osmium tetroxide is well known for smelling vaguely of chlorine. And if you smell that smell, you are about to go permanently and irreversibly blind if you do not die.
Wow.
And this is an oxide powder, right? That is so volatile that it can just murder you if it's in the same room as you. So some people are very, very unhappy about the idea of working with osmium, but most of the materials that I work with are so very far from like that level of dangerousness. But there always exists this non-zero possibility that there's some osmium tetroxide in your sample at a very low percentage, which might be enough to like cause you great sickness. So that's one of the fun things about working with it.
Wow, that's pretty intense, to be fair. I mean, I've got all sorts of stuff in my lab, thanks to the research that the professors do. So it's amazing what I've got. I don't think I've got any of that. But yeah,
probably not. But you'll have loads of arsenic, right? Because the iron arsenide superconductors are super popular.
Found a bunch of thallium recently, just lying around. I've got loads of thallium knocking around. And it's interesting with this sort of not being happy working with them. We had a release of chromium-6 in a lab when I was a postdoc. Yeah, exploded everywhere in the lab.
Oh, great.
Yeah.
I bet Sandra Bullock was there in a heartbeat.
Not so much. We had, within 20 minutes, we had 3 ambulances, 5 fire engines, hazmat unit, police. It made it into the local papers in Switzerland. The lab was shut down for deep cleaning, even more deep cleaning than a corona clean down, I think. So I learned a lot about chromium-6 oxide then, and just how, and we didn't even know. So something exploded, and it turns out that that's what it was packed with. So and we didn't even know that.
God.
Yeah, it was so exciting times. I mean, it was a good story.
I mean, these always make good stories, right? Like, my favorite historical one is when an industrial amount of dioxygen difluorine was spilled, which is a chemical famous for its ability to burn sand and concrete. And in doing so, releases a very exciting amount of hydrofluoric acid gas.
Oh, wow.
It's just the most noxious stuff. It burned through the concrete floor of the building and about a meter of sand underneath foundations, and caused the evacuation of both the building and the nearby town.
Wow. That's... Yeah, it's amazing. This, if you've been in science for a while, there's so many of these stories. There was a factory we were working on, and formaldehyde was just sort of a byproduct of the process we were doing. And then we found out that the extraction fan was, and yeah, they were just extracting it outside. But it turns out that they actually had it wired up wrong, and it was pumping it into the factory and out. So there's loads of these.
But one of the sister university of my undergraduate university had got a new chemistry building because they accidentally blew a hole in the side of the old chemistry building because they had an organics fume hood that was hooked up to a perchlorates fume hood. And then one really hot summer,
Oh, wow.
organoperchlorate explosion.
Wow.
But the new chemistry building was great.
Oh, that's good. Yeah, I think, what was it? A lab that a friend works in Sweden. I know that they've designed the building so that if it explodes into the forest, which is sort of closed off, no one can go in, and it's sort of designed to go that way rather than, into the campus, which is fun. The fun stuff of science, I love it. All these stories.
Sorry. I think you asked me what's interesting about osmium though, as opposed to terrifying.
Yeah, I know, but the terrifying stuff's fun too.
So, generally speaking, the way atoms behave in materials are determined by what interactions we can ignore. Or rather, the ones that you can't ignore, I guess, determine how it behaves. So, generally speaking, what you do is you start with the idea of an atom as it exists in free space. So you can solve the Schrodinger wave equation. It might be a bit complicated. You might have to do some approximations, but there is the notion of the free atom as it exists in a vacuum. And then once you put this into a material, there's this, what we call the crystal field, which is the electrostatic interaction that the atom feels based on all of the atoms around it. And if you ever looked at a picture of what orbitals look like in an atom, you might see that some of them look like spheres, some of them look like dumbbells, some of them look like a cross, and so on. And so an electron which sits in one of those orbitals kind of, to some approximation, lives inside that shape. So maybe it's a dumbbell which points along an axis. And if you are an atom with an electron occupying an orbital which is like a dumbbell pointing up and down, and you have a great big pair of oxygen atoms above and below the atom, which have a huge electrostatic repulsion on your central atom, then an electron which lives in this orbital is going to be really unhappy, because a lot of the time it's going to be seeing this huge repulsive electric field from these two oxygens. So crystal field theory basically says that electron is probably going to prefer to live in an orbital which is not pointing directly at a giant negative charge. And this is the sort of first interaction that you usually consider. There is also an interaction which we consider usually in metals, but in reality it exists in like every material, which is that if you have, imagine like a chain of atoms, and it's really sort of intuitive when you think in a metal, the electrons are so-called like free, or some of the electrons are free. But really, the electrons live on the atoms most of the time. So what we say is that there's a hopping from one atom to the next atom of the electrons. And so there is also an interaction which opposes that, which is just from like the Pauli exclusion principle to some extent, and it's also to do with the Coulomb interaction as well. Because electrons are negative charges repel. So if you have two atoms hopping in the opposite direction and they both hop onto the same atom at the same time, Pauli exclusion principle says that they can't be in the exact same orbital and the exact same spin, all the same quantum numbers can't exist. And the Coulomb interaction says that they probably don't want to be even in the same orbital, because then they'll be really close to each other. So essentially what it's saying is that they want to move around, but they don't want to move onto the same atom at the same time. And so we have these energy scales like the electrostatic repulsion that the atoms feel, the energy scale associated with electrons moving from atom to atom, the energy scale associated with electrons both sitting on the same atom at the same time in the same orbital. And we have another energy scale, which is usually we call the spin-orbit coupling. And it is to do with the atoms themselves. And it's basically how relativistic the electrons are. Because it's probably not worth going into too much detail, but essentially, like, because of relativistic invariance, essentially, if the electron is relativistic enough, then it sees its own angular momentum, more or less. And so its spin becomes correlated to its angular momentum, which is determined by the orbital that it sits in. And so you basically get a situation where you can't just have any spin and occupy any orbital, and it doesn't matter. All of a sudden, there is a preferred spin for certain orbitals, and the atom prefers to have a collection of electrons which obey a set of rules, which are determined by who has the lowest energy, which is always what determines like what is your ground state. But in this case, it's just a sort of relativistic effect. And relativistic effects for atoms are more important for heavier atoms. So this is why you don't care about it for hydrogen, helium, iron, copper, but you do care about it for big fat atoms like iridium and osmium, and for all the rare earth elements as well. It's just that in the rare earth elements, you really only care about this relativistic effect. And the crystal field effect is pretty small, because the electrons which do the business of determining your physics in a rare earth element are inside the atom, and you have a lot of electrons outside of that, which then shield you from your crystal field. And they're also stuck on the atom, so they don't participate in jumping from atom to atom. So the only thing you really care about is just this relativistic effect. Everything else is kind of like a small impact on that. The reverse effect is true for transition metals like iron, where the crystal field effect is really the thing that sets a lot of your physics, because the electrons which are important are quite outside, or far away from the atom, so they really feel this electrostatic force. They also tend to hop fairly easily. So in a lot of cases, it's just you have crystal field, and then maybe you have some important considerations based on the hopping and the repulsion. But crystal field comes first, usually.
Yeah.
Then you get, they do have like quite a strong repulsion, but like it's not super important. Then you have the osmium, iridium sort of like, they're also technically transition metals, but because they're 5Ds, they're talked about very differently because they're so much further down the periodic table. But here, your relativistic effects are really big. The atoms are sort of fat and hazy because they've got so many electrons. So the crystal field effects are a little bit like reduced. The hopping is not quite so strong, and the repulsion is also not quite as strong as it is in regular transition metals. So you have your relativistic effect, your crystal field, your hopping, and your Coulomb repulsion from double occupancy, and all of these energy scales are basically the same. And so when it comes to predicting, or what we like to do is basically say, I will throw away as many of these as possible. I will solve that problem, and then I will modify the solution slightly by turning back on really weak effects from all the things I threw away at the beginning. And this is not always easy, but it's certainly tractable. So you can make some good progress.
Yeah.
But when you get to the 5Ds, you can throw away none of those things, and you have to solve the most complicated thing possible straight up. So lots of new things can happen. Lots of new techniques are required in order to really solve the problem properly. Because ultimately, the more things you have to consider at the same time, the harder the solution is. And not in like a linearly additive way either, unfortunately.
Yeah, yeah, I know that. And I think it's interesting because we sort of flippant. I asked before what was the purpose of these materials that you're looking at and why you're looking at them, and you said it's blue sky. You're looking to see what the case is, but I think that's really and I think that's something that people don't understand with science is that sometimes this blue sky research, this is where we find out more things about the world around us. I mean, even superconductivity was just, noticed by accident over 100 years ago. Because someone decided they wanted to cool down liquid helium and just see what happens. So we don't know what the implications of the research you're doing is, and you'll be able to apply it. And I think it's really interesting that you're now specifically using the skills that you've learned over the last few years to design different materials, because then once we understand materials enough that we can start designing, that shows that we understand them to a good degree, and we can try and solve particular solutions depending on what we need.
Yeah. It wasn't even just regular superconductors that were sort of found by accident either. Even the high temperature stuff, they weren't looking for superconductivity when they designed the cuprate superconductors. They were just making ceramics and seeing what happened.
Yeah, I mean, who thought that insulating ceramics would become superconductors? Yeah.
This was exactly it. Actually, this is also one of the reasons why people got interested in 5D oxides, because iridium oxide there are some iridium oxides which are quite similar to the copper oxide superconductors. It's just that you've got this extra degree of freedom with the relativistic effects. So it's possible to see kind of what happens when you turn on extra interactions. And usually people are just hoping to learn a little bit more, because honestly, we've been working on the copper oxide superconductors for 40 years. And, I don't care what Bob Laughlin or Philip Anderson say. Like, it is not a solved problem. Otherwise, we would probably know a lot more than we do. It is a very overdetermined problem. There is a billion experiments that have been done, but ultimately there are still some significant outstanding questions about like why they do what they do, when they do, how they do it, and even what exactly they are doing in some bits of their phase diagram. It's not clear.
Yeah, I really hope it isn't solved, because we've just put a big bid in for me researching cuprates. So yeah, that's what we said as well, and hopefully I'll be able to sort of add a little bit more to that in a few years, if you get the funding, of course.
Yeah. Well, so it's quite funny because there was an attempt to make something which is an exact analog of copper oxide superconductors, but with more spin-orbit coupling or more relativistic effects, because you can do this if you make silver difluoride. But silver difluoride, on exposure to moisture, explosively turns into hydrofluoric acid, like all good chemicals. So some colleagues of mine actually did an experiment on a, quite frankly, heart-stopping amount of that stuff a little while ago, and they were basically in full hazmat. And it was in a sealed container that like nobody was allowed to disturb, and all basically to see if like it behaves kind of like you would expect copper oxide does, but with some additional relativity thrown in.
Huh. Interesting.
And this is why we prefer iridium.
Yeah, which it's interesting to think about, though. I mean, the nice thing, so the sort of techniques, because I'm, doing thin film, making thin films, the nice thing is we can make a thin film in a vacuum and then put something on top of it to basically sort of shield it from anything else. And, we do that quite regularly. So sometimes we can actually get to play with some of these materials that we probably shouldn't. And you've given me ideas, if I'm perfectly honest. But
well, at least with thin films, like if it does go bad, there's not enough of it to probably murder anyone.
Yeah, that's fair enough. I mean, we've already got a fluorine-based laser gas in our lab, so why not just keep on telling our new students, like, oh yeah, no, it's not toxic, it's fine.
Fluorine is totally safe. Yeah. What are you talking about?
It's a low quantity, it's a low percentage. We're all right, but yeah.
Don't ask what happened to the last PhD student.
That's why the cupboard's heavy.
One of the things that is a big problem, though, is that, or for us at least, is that we would usually love to look at thin films, but neutrons don't really see them because they're thin. And neutrons just more or less don't care that stuff exists. So you need a lot of stuff in order to scatter enough neutrons off it. But one of the really nice things about cuprates is that the energy scales involved are high enough that you can use X-rays instead. And actually, one of the things that I have the privilege of having sort of like watched for my entire career is the explosion of X-ray based techniques for doing what neutrons have been doing for a really long time. It's just that the limitations for X-rays are sort of the exact opposite of the limitations for neutrons. So you get very few systems where you can do really good physics with both X-rays and neutrons and sort of put those on top of each other and see what you get. Usually you're looking at like, this end with neutrons and this end with X-rays, and you have to kind of imagine what's in between.
But this is exactly why we can't just have one technique, whether it's production, whether it's measuring. We need multiple techniques, and we use the ones that are most suitable. So, that's the point. We've got more tools available. And I think that's really, really interesting. And yeah, we also want to see what happens to some of our thin films with neutron damage, but of course we can't really. So it's
neutron damage is a bit easier because that there's the chip IR facility at ISIS.
That one, no, but I would imagine the other the people working on that project do? I would assume, but tell me more.
So it's what we use to test what would happen if you put computers in space, that kind of thing, or like aircraft mechanics up in the outer atmosphere.
Okay.
And basically what they do is they expose it to the entirety of the spallation reaction. So normally there's a humongous amount of shielding and filtering and everything else in between where the high energy protons are smashing into the target and spewing off neutrons, and where you actually collect your neutrons at the end. Whereas chip IR is literally just they open the gates. Which is really funny because when chip IR is on, you can kind of tell on every single instrument in the facility, because even if your instrument is off, you can register some slightly elevated background counts.
Right. Wow.
From
that's so cool.
Hundreds of meters away through concrete. But yeah, it's not a lot, thankfully. It's well within safety margins.
Good to know. But, I was looking at moving closer to that area, so anything
that's made it as far as Didcot is going to continue straight through you. It's fine.
That's true. That's great.
Yeah,
that's so cool.
I think they can get the equivalent of decades worth of high energy particle exposure in a few hours.
Wow! Oh, that's so cool. Because say the people that I run the lab for, they're doing some of these really long-term experiments and stuff like that. So that's really cool. And like I say, that's not my area, so I don't really know about that. But that's good to know. That's interesting. We've been talking for a little while, and I want to talk about the diversity work. But I do just want to ask before we do that, how is it? Because I think this is a really interesting part of what you're doing. So you were talking about measuring properties of materials, and you're using X-rays or you're using neutrons to do that. Can you give us a brief overview of how you're doing that? What you're doing with that?
Yeah, the sort of simple version for neutrons is two different things. So essentially, if you have a really regular lattice of atoms, which you get in a crystal, then you can bounce a neutron off that as if it was a photon. So basically, have you covered diffraction or something like this?
I haven't actually. No.
Okay.
I should, but I haven't.
I won't go into it too much, but essentially, a neutron can behave like a wave, just like a photon can. And if you have a regular lattice of atoms, as you get in a crystal, then when the neutron interacts with this, it can scatter off it just like any wave could, assuming that the wavelength of the neutrons is very similar to the spacing between the atoms, which is very important for any kind of interference effect.
Yeah. And
as a result, the way that the neutrons scatter from the crystal is very characteristic of the spacing and the arrangement of the geometric arrangement of the atoms. So this is what we call diffraction. Mm-hmm. And you can do this with X-rays, you can do it with neutrons, you can do it with electrons. And what you see depends on what you're doing it with. So photons mostly see electron density. So they don't really see atoms per se. Mm-hmm. They see where the electrons are, which means that if you do the same experiment with neutrons, which really only see the atoms, you get something which is slightly different than if you did it with X-rays or electrons, which also see the electrons. So particularly if you have what we call a covalent bond, where the electrons are sort of shared between two atoms, in a very good experiment with photons or electrons, you can really see the difference between the scattering that you get from a covalent bond, where you've got electrons all the way across between the atoms, and neutrons, where you just have where the atoms are. Because the neutrons really don't see the electrons very much. Mm. The only thing that the neutrons see which comes from the electrons is the magnetism. And this comes back to that thing that you were talking about earlier with spin. Mm-hmm. And this is because electrons have a spin and neutrons have a spin. And so the neutron spin can scatter from the electron spin. And what this means is that you can see something which is different in an experiment which uses neutrons than you can in an experiment that uses X-rays, which, to a very good approximation, and I will probably be crucified for this, don't see spin. They can, but like not very well.
Yeah.
They can see it, but it's like way off in the distance. So what happens is, if you imagine you have a magnetic material and you're looking at it with X-rays, and let's just say that it's what we would call an antiferromagnet. So every atom has a spin, and every second atom, it's pointing in the opposite direction. It goes up, down, up, down. If you look at this with X-rays, all it sees is atom, 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 atom. If you look at it with neutrons, this atom and this atom are not the same. So it will see something where the identical atoms are twice as far apart as you see with the X-rays. And so neutrons are the probe that we really prefer when looking at materials which are magnetic. And it gets even more so when we're looking at what we call the excitations of the system. So if I take the case of like a really simple magnet, like a bar magnet, where every atom is pointing in the same direction with its spin, this is what we call the ground state. So the lowest energy state is all the atoms pointing in the same direction. And there are an infinite number, essentially, of excited states which have an energy which is higher than this, because it costs you some energy to create them. And the lowest energy excitation is you just flip one of your atoms so that the spin is pointing in the opposite direction. And this has an energy cost because the reason they're all pointing in the same direction is that they gain some energy by doing this, and they would lose it by doing this. And so the energy cost to flip one is basically twice because you have two neighbors, or maybe 4 times because you have 4 neighbors, or so on. And so what you can do, rather than just measuring where all the atoms are and what directions their spin is pointing at, you can look only at the neutrons which changed their energy when they scattered from your crystal. Because they're the ones that have lost some energy to flip one of your spins. And by knowing how much energy it costs to flip a spin, you learn how much, what is the strength of the interaction between adjacent atoms. Because if, for example, you have like atoms in a chain where it's up, 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 the cost to flip one is 2 times the energy between the atoms because you have 2 neighbors. So flipping one of them costs you twice whatever the interaction between 2 atoms is. Or if you have a square and you flip one of them, the cost is 4 because you have 4 immediate neighbors. Or if you have a cube, it's 6. So if you divide it by the appropriate number, you find out how big this energy is. And in more complicated magnets, it's actually much more difficult to do this. And if you ask most people what your data for inelastic neutron scattering is like, which is what this technique is called, horrifyingly complicated is usually the sort of summary of what they will tell you, especially because it's 4-dimensional. And trying to examine 4-dimensional data, which is very complicated and only some of it is meaningful, is nightmare-inducing. But it's very nice because if you finally get a handle on it, you can tell basically everything there is to know about the magnetic interactions in your material. And that allows you to really deeply understand what is going on and why it has the magnetism that it does.
That's really interesting. Thanks. It's interesting. So there's a whole bunch of different techniques, and in my lab we have an X-ray diffracting machine. So I will talk about that at some point. And we use magnetoforce microscopy as well. We've got a cryo MFM, which is a different way of measuring magnetic fields as well, and maybe I'll go into that in a future video as well. There's so many different techniques and they're all useful for different things, and this is it. We're building up a picture by using a combination or the right one for the right job, basically. So that's really cool. And like I say, science is complicated. Apparently.
I do indeed have a paper that I'm trying to get published, which we spent 7 years working on with about 80 different experiments.
Wow. Okay, yeah, that's a paper and a half. So, just to sort of, I've kept you for 50 minutes already. Would you believe it? It's gone really quick. For me, anyway, it's like a free lecture, and some of it's telling me stuff that I'm supposed to know, which is great. But so we did say at the beginning that we met, at the LGBT seminar, and that's where we first started chatting. So you are very active in outreach, diversity, and trying to be more inclusive. You actually, there was also you sort of wrote an article recently which was put out criticising one of our learning societies, the Institute of Physics. Why is diversity, why is inclusion and equity important to you? What effects have you seen or seen on people around you as a gay man in physics? Has there been stuff?
So I may be a gay man, but mercifully I am a cis white gay man. So I avoid most of the issues that people are expected to face, which will prevent them from really thriving in academia. But I see the negative effects of discrimination experienced by a lot of other people. And it doesn't even have to be overt, although I believe that it is overt much more often than people would like to admit. But it is extremely difficult when, in order to do your job, you have to basically run twice as fast to get half as far, just because people don't respect your opinion as much because of how you look, or because you have a disability which makes you slightly difficult to work with, or because of the color of your skin, or you dress in a particular way. Like, there are so many things that people can hold against you for no valid reason whatsoever, which is, I think, what upsets me the most about scientists when they discuss diversity and inclusion, because so many of them are under the impression that we are taken only at the face value of our ideas and our opinions. And yet, so many times I have seen somebody's ideas dismissed not because of their idea or the quality of their argument, but because of who presented it and how they presented it, the tone that they used to present it. If we really, really only cared about the logic and facts behind somebody's science, then this would never come up. But unfortunately, it comes up all the time. And if you have never seen somebody say, "Oh, I'm not so sure I trust those results because they're from insert lab here, insert country here, insert institution here, insert race here, insert gender here," you're just not paying attention if you've never seen that happen, because it happens all the time.
I completely agree. It's and I think you undersold it. I think even it was nice to sort of acknowledge the privilege that you have, but you can't. It's also true that even cis white gay men still can experience more discrimination. There's been papers that have shown that. We know that, even taking into account gender and race, LGBTI plus people are still more likely to drop out. And of course, for a lot of your you know, for a lot of my career, I was pretending to be this straight white male, but that's because I wasn't coming out. That's because I was in the closet. That's because I was hiding. And there's a lot of emotional baggage with that as well, which does impact your work, or it did for me anyway. When you don't feel that you can come out, when you're hiding an aspect of who you are.
Yeah, I guess that's something that I do always forget, because it is so invisible. That even if you are a cis white gay man, you maybe not be out, in which case dealing with your colleagues every single day becomes like this minefield of like, oh, don't use that word. It will make them know I'm gay. And I was bullied as an undergraduate for being a loud gay man by somebody who was in the physics society at my undergraduate university. Although they got what's coming to them. So
slip some osmium.
I wasn't working with osmium back then. We just took over the physics society and excluded them, basically. It was great.
Yeah, so we know, and I don't want to belittle, I know that sort of the more and different diversities affect us to a higher or lower degree. And of course, if you're intersectional and you've got you're from a number of different backgrounds, then it's even worse. But I think, and I feel like this is something that we do quite a lot, especially if we're a little bit older. We just sort of, our baseline is so wrong. Our baseline, you know, we're like, oh yeah, no, we don't have it as bad as these people. It's like, yeah, but that we still have it worse than, you know, the rest. Yeah. And so it's important to sort of acknowledge that, no, you know what, it hasn't been perfect, and this is why we're still fighting to improve it for the future.
I mean, especially in academia, where you get so used to being ground into a fine paste every day, you lose a lot of perspective about how nice and welcoming a place could be. And this is actually something that I've really noticed as someone who is dually employed by a national lab and a university. The difference in how you can be valued as a person and an employee or as a scientist is quite different, is quite broad. I only have one line manager who genuinely, I have a line manager and a senior line manager on one side of my job, who regularly praise me for the work that I do in fostering diversity and inclusion, doing outreach, speaking to like visiting school kids from inner London, like that kind of thing. And they encourage me to put this on like my key targets for the year of things that I should do, and support me like financially when I try and do these things, and make sure that I'm never out of pocket for like going somewhere and speaking at like an LGBT event. And I can tell you for free that that's not the university that does that.
It's the same in my lab and my department. I'm in a really amazing group, but it's the group, it's the department. Yeah, that's yeah. I mean, that's a big thing. And how are you finding? So we mentioned sort of briefly about sort of learning societies and stuff. How are you finding the societies? I don't know which societies you're involved with and what you're seeing with them and how they are looking to address issues of disparity disparity of equity, basically.
I feel, generally speaking, there are always people within an organization who are really seriously motivated to make things better. Even the one that I recently criticized deeply and savagely, I know that there are people who are heartbroken reading what I wrote and reading the response to what I wrote, because they put their heart and soul into trying to make a real positive change. And they probably felt a bit maligned by what I said, although what I said was directed at the executive, not at the people on the ground. And I know, because I read some of their responses, that they felt ignored by the executive when the executive responded to what I wrote, because they did not really seem to appreciate the point even of a lot of the programs that they do in diversity and equality. They're just using those programs as shields and sound bites and letters of intent and statements of like goals, instead of like actual track records for systemic change that they have made. And it just increasingly seems clear that there is, in some cases, a really savage disconnect between the people who are in EDI roles and who are actually putting forward the policies and doing the events, doing the hard work, and the people who are at a level above that, who don't necessarily appreciate the work that is being done by their EDI teams, or necessarily value the work that they're doing, or even really obviously support it.
Yeah, I tried to make a point at the time, because it was ironic that the day that letter came out, the same organisation was also advertising a talk by me that I was doing for them, and I tried to make the point that there's amazing people doing amazing work. You've got an awful lot of amazing volunteers in the society doing a load of amazing work. We're all putting a lot of effort, a lot of time, and we know what we're talking about. So the people that are making certain decisions, you've got to listen to us, otherwise we're just a paper ticking exercise. You've got to consult, I think.
Yeah, I mean, like so many of these things, you have to be open to criticism, because you will fuck up all the time. Like, even when, and this was so perfect, when I criticized the Institute of Physics on Twitter, I inadvertently used an ableist term because I called them tone deaf. And somebody very politely and privately messaged me and was like, I really would like to retweet what you've said, but... And I was like, I'm such an idiot. But you have to be willing to be told.
I completely agree. And we were both, at the beginning of the year, we were, involved in some tweets where... and it was obvious in hindsight, but at the time we were trying to make a point to try and be more inclusive, and someone said, "Oh, your language is tone deaf." Oh God, I've just said exactly what you said. Don't. It's because you just used it. And my apologies. It wasn't taking into account, the lived experiences of a lot of people from different races, and so what I realise now, my flippant comments actually had more implication, even though I was trying to do the right thing. But I listened to that, and I think about it more now, and hopefully that means that stuff I do in the future is going to be better as a result. Because this is it, we get to work with amazing people. We're both part of Tigers, where we have such a network of different people from different backgrounds, and I think that's something that's really important for me. I'm not just fighting for LGBTI plus rights in STEM or working class rights in STEM. It's everyone. I want everyone. I want science to be better, a better place, and you're the same,
Yeah.
And so making sure that and one nice thing about the group is that we will listen to criticism when we get called out, and there are right and wrong ways of criticizing.
Or, at the very least, more and less helpful ways.
Well, yeah, exactly. We're all human. We don't want to be viciously attacked for trying to do the right thing. But I love that range of voices that we get. It's amazing, and that's why I wanted to do these videos, to show that there is such a wide range of people in STEM. And they're not just a diversity. They know their science. They know what they're talking about. They know their engineering or field. And they do know what they're talking about, and they've got so much to give. And if we could just get on and do that, but we seem to spend a lot of our time needing to talk about diversity right now. And I do so happily, and I think you do too.
I mean, absolutely. I enjoy trying to reassure people that there is a place for them.
Yeah.
And that they will be welcomed and respected and valued. And I enjoy even more when I feel like that might be true.
I think we discussed this recently. You know, it's for me, it feels like I'm trying to make it better for people coming up, not necessarily for me, but for the next generation or whoever, you know, whatever generation counts as. But it's making sure that it is better going forward. And it does benefit science. The more people that are involved in solving the equations, solving the problems, you know, the more brains we've got on something, the better. It's as simple as that. So, yeah, big topic, but you're doing amazing work, and you've had a massive, I'd say you've had a really big impact, and I'm certainly feel so lucky to have you as a friend and a sounding board, and both on the scientific and the diversity front. I had you looking over my superconducting electromagnetism stuff the other day, so which actually I'm probably going to put out today on the day of recording this, not on the day of releasing it. So there you go. Yeah. Anything else you want to say before we wrap up?
No, I think we've covered a lot of ground.
Covered loads. It's awesome. So, well, thank you so much. Thank you so much for joining me. So what I'll do is I'll sort of switch for thanks screen in a second. But yeah, so thanks everyone for watching. Thank you, Andrew, like I say, so much for taking part and being my guinea pig as well. Hopefully, I'm just hoping that all the sounds have recorded properly. The next 10 minutes after we get off the call is going to be very nerve-wracking to make sure everything's recorded. But no, thank you so much.
Bye.
Cool. Well, hopefully you enjoyed that. I did. I know I ramble about whatever the heck I feel like, but you know what? That's what I want to have from a conversation with my friends. Hopefully you learned something about the science that Andrew does, and also, you know, why it was that I was chatting to them in this segment. And yeah, like I say, there's a website link below for Andrew and his Twitter feed, so give him a follow. And like I say, if you like this video, you know, feel free to like, subscribe, share. It really helps out a small YouTuber. I've been putting a lot of time and effort into these videos, and so it's nice to sort of get the figures and the followers, but you know, that's up to you. Of course it is. So yeah, with that, I'll see you again. I've got a couple more recorded. I've got very different fields and different people coming up. I'm going to try and release these every 2 weeks, so it's going to be a real mix of people. I think you already saw my chat with Izzy Jessing a few weeks ago. Well, I'll be talking to her again about her science, and because we didn't really get to talk about that in the previous chat. So and we've got other people coming up as well. That's Clara Nellis will be next, who is a kind of particle physicist at CERN. So I think that's really exciting. All right, until next time, thank you so much for watching. Take care and bye bye.